Precalculus lesson 1.4, shifting, reflecting, and stretching graphs. In this lesson, you shall learn how to recognize graphs' parent functions, use vertical horizontal shifts and reflections to graph functions, and use non-rigid transformations to graph functions. Those are just dilations, also known as when you stretch or when you shrink a graph. Okay, so we have to know our parent functions, because all we're going to do here is we're going to memorize our parent functions, and then we're going to make them bigger, smaller, move them up, down, left, right. So that's the general gist of how you graph things. So we start with our basic parent functions here, like our linear function. I said it right there, our linear function. Right, this is like slope-intercept form, y equals mx plus b. This graph you know how to do. You know how to stretch a string, you just didn't know you were doing it. Then we have an absolute value function here. Right, looks like a v in the middle. That's a graph we're going to do a lot of. We have our square root function, starts in the middle, kind of makes like a curved sign. Our quadratic function, x squared. We have our cubic root function, our cubic function, right? X cubed. Cubic function, and our rational function, 1 over x. Looks like this. So these are all the parent graphs. And what we're mostly going to do is we're just going to move them up, down, left, right. So we'll start with like y equals square root of x, and then we'll do like a plus 3, and like, okay, what does that do to the graph? That's what this lesson is all about. So let's start off with our vertical and horizontal shifts. So the general rule here is anything that's on the outside. Right, so here's my function. If you're on the outside, that's what I consider the outside. It affects the y values, and you follow what it says. Right, so y value means you're going to go up and down. So if it's a plus, you're going to go up, negative, you're going to go down. So you kind of see it, right? Vertical shift upwards, vertical shift downwards. Notice how it's on the outside. Anything on the outside moves you up and down. And you just follow what it says. Trickier thing is when it's on the inside. Something like this. So inside affects the x values, and you do the opposite what it says. If it says plus, you go left. If it says minus, you go right. So you can do the opposite value there. So if you see here, right, when it's a minus, it's like we're like a plus c, so you're gonna go right c. When it's a plus c, it's like a negative c, because you're like solving the inside. If you'd like solve this, you like add c over, you subtract c over. So inside opposite, and it goes left and right because it's an x value. So inside x, opposite, outside y, follow is a key for me. So when it's on the inside, you do the x, then you do the opposite. When it's on the outside, it affects the y values, and you follow. And again, y is short for going up and down, x is short for going left and right. So let's do a couple examples. Okay, so this first one, that's a cubic graph. So you don't have to do this, but I'm going to draw the original graph, like the parent function, dotted line. So you get to see what the original looks like. All right, so a big part of this is knowing your parent function. So that's like a normal x cubed graph. And then what I do is I look here and I go, okay, is this on the inside or the outside? So that's on the outside. That means it affects the y values, and we're going to follow what it says. So in this case, y moves up and down. So it's a negative, so we're going to go down 1. So all we're going to do is get our graph here, and we're going to go down 1. Technically, every point goes down 1. Like that goes down here, that goes down there. But we're just going to draw a sketch. So something like this. I don't know why it keeps on erasing. So something to that effect. That's how we draw that. Next one, another cubic graph. I guess they're all going to be cubic graphs. So I guess let's first just draw the parent function, all of them. Again, you don't need to do this part. I'm just drawing it. I think it helps see, visualize it. And you can see it's not a perfect graph there. Okay. So this one I would say is on the inside. Inside affects the x app, and you do the opposite. So what I mean by that, it's not like really like a negative one. It's like a positive one. So we're gonna go right 1. So all these points in the graph are gonna move right 1. So we're gonna be like right here. So kind of like this. So it's that effect. And then the last one here does both things. There's an inside and there's an outside. So this guy tells me to move up 1. it's going to tell us me to move left 2. So it kind of looks like this. Like if you normally start at 0, 0, on this one we're going to start at 2, 1. Negative 2, 1. Right, because it's left 2, so we're going to go minus 2. So instead of starting at 0, 0 like we normally do, we're going to start at negative 2, 1. Right here. And then we just draw our cubic graph. By the way, you could have done that for all of these. Like this one would have been, we went right 1, so 1, 0. And this one we went down 1. So 0, and then, right, nothing on the inside, so nothing on the x. But then we went down 1, so our y is down minus 1. So you can always think about it that way. Like that's our starting point. Normally 0, 0. Or we're moving down 1, so our y went down 1. So you start there. Right, normally 0, 0. We're moving right 1 on the x, so x value gets plus 1. And then here, right, normally 0, 0. We're going left 2, so minus 2. Inside opposite. Outside follow, up 1. I guess it looks like that. Okay, how about going backwards? What if I give you a graph of x squared in this case? How do you find the equation? So in this case, I always think about the generic function. It looks like this. Right, and this guy's just how much you're moving left and right, so how much you're moving up and down. These are x values, these are y values. And then this function here, in this case, it's x squared. So like if we're doing this one particularly, it looks like this. X minus h squared plus k is what this graph kind of looks like. Right, because this one happens to be an x squared, so it looks like this one particularly. And all we gotta do is basically find the vertex. So like this one right here is a basic one, nothing changes. What happens here? We went up 4. So our vertex is 0, 4. So you could just, if you know it, you just go, okay, y equals x squared plus 4. Right? We went up 4, so it goes on the outside. If you don't like that, you prefer this, well, this is my h and this is my k. Just plug it in. 0 and 4. And you get y equals x squared plus 4. Right? It works both ways. So the same thing here, right? If you know it, you just go, okay, wait, I went left 2 and down 1. And then you can set up the equation appropriately. So like inside opposite, x plus 2, and then outside follow, minus 1. So if you want, just do that. If you prefer, that's your h and k. Once you find the vertex, just plug it in. So this is going to be negative 2 and negative 1. And then you simplify it, right? 2 negatives make a positive, so I would get x plus 2 squared minus 1. So you get the same thing either way. So that's the key to going backwards. If you know it, just do it, right? Just inside it, outside. If you don't, find the vertex, plug it in. Okay, how about reflections? So that's when you see a negative in front of it. So I probably teach this a little different than most people. So the technical term is if you see a negative on the outside, we call that a reflection across the x-axis. That is a technical term. The way I look at it is if it's on the outside, outside is y, so that's up and down. So we're going to call that a vertical flip. So you're going to flip up and down. So if you see here, right, here's my thing. If you flip it up and down, like you said, negative on the outside, you're going to flip it up and down. Look what happens. You flip it across the x-axis. Right, that's why it's called an x-axis flip. So negative on the outside is x-axis flip. I just think, okay, outside is y, that's up and down. We're going to flip it up and down. You do have to flip it across the axis, so you don't just like flip it up and down. Flip it across the axis. So same thing for the inside. When it's on the inside, I think inside is x. So left and right. So I call that a horizontal flip. So I call that horizontal flip. So if you look at it, we'll flip it left and right, you flip it across the y-axis. So that's the way I think about it. If I see a negative on the inside, inside's x, that's left and right, so we're going to flip it left and right. If you see it on the outside, outside's y, up and down, you can flip up and down. So let's look at these. So we're going to find the equation first. So if we look at this one, y equals g of x. So this is, we want the equation first. So this is an x squared graph. So how do they flip it? Well, if you look at this, if you kind of think about it, like flip it back the correct way, what equation would that be? That would be x squared plus 2. So all we did was flip the x squared, because the first thing you do is flip. So we flipped it upside down, then we moved it up 2. So my equation here is going to be f of x equals negative x squared plus 2. Right, because you flipped it and then you moved it up 2. So same thing here. Flip's always the first thing you do. So you notice how it's upside down? So that's going to be a negative x squared again. What did they do this time though? They moved it right 3. Right. So plus 3, but remember it is inside opposite, so it should be negative x squared. Negative x minus 3 squared. So that should be our answer there. Again, if you don't like that, whoops, you can always think about the normal function, right? The normal function is x minus h squared plus k. So what's going on here? I see it's flipped. First thing I notice is flipped, so there's a negative on the outside. And then what's my vertex? 3, 0. So h is 3, k is 0. So I get negative x minus 3 squared plus 0. So either way works. All right, if you could see and go, what's going on? Boom. If not, use the general form, find your vertex, plug it in. Compare the graph of each function with the graph of its reflection. So we're just going to graph these real quickly so you can see it. So square root of x. So that basic one looks kind of like this. It's not perfect, but that's my sketch. The next one, notice how the negative is on the outside. So this one, let me do some purple. That's a vertical flip. So I'm going to flip it up and down, right? Or flip it up and down. So it's kind of like this. Again, not perfect, but that's what that one looks like. This is negative square root of x. This is just square root of x. Okay, the next one, the negative is on the inside. So inside is a horizontal flip. So we're going to flip it horizontally, left and right. So I'm going to flip it this way. Because again, we're starting with this one, right? We're flipping this guy. So I'll flip it that way. So it's look kind of like this. Again, not perfect, but that's the general idea. So like that. Right, flips them left and right. The one right here. Notice it's a negative on the outside. So flip down, vert flip. So it's going to look like this, ish. And then we're going to move it left 2, right? Inside opposite. This is inside, x, opposite. We're going to move left and right. So we're going to go left 2, then it's open down. So we're going to get our normal graph here. That's our normal one. We're going to move left 2, right here. And then it's an open down because there's a negative. So the first thing you're supposed to do is flip. So technically you flip it down like this first and then you moved it. So it looks kind of like this. So that's how those work. Now let's look at non-rigid transformations, which are just dilations. All we're going to do is make our graphs bigger and smaller. So the general rule is right here. So if y equals a f of x, that's on the outside. So it's going to affect the y values. And the general rule is if a is bigger than 1, it makes it, we call it a stretch. We're going to make it bigger. If a is less than 1, it's a shrink. We're going to make it smaller. So if you look at here, h of x equals 3x. I'm like, oh, it's a vertical stretch of 3. So how does this work? First, let me graph the original one. I'm going to try to graph it nicely this time. So it looks like that. We'll say it goes through points 1 and 1. We'll look at 3 and 1. 3 and 3, sorry. Can't do math sometimes. Over here, like this. So we'll look at 1 and 1 again. Well, negative 1 and 1. And then negative 3 and 3. So like that. So that's our normal, that's a normal square root of x graph. What does this guy do? Well, it's on, that 3 is on the outside, so it's going to multiply our y values by 3. Right, again, why the y values? Because it's on the outside. Outside affects the y values. So we're going to get all the y values here and multiply by 3. So 1 times 3 is 3. So it becomes that guy. 3 times 3 is 9. So it becomes like up here. You can start at 0, 0. 0 times 3 is 0, so it stays right there. Because that was 0, 0. Right, it still stays. Negative 1. Well, negative 1, 1. 1 times 3 is 3, so it goes up here. And then 3 times 3 is 9, so it'll be up here again. If we connect all those, you get what we call a vertical stretch. You like stretched it by 3. You multiplied all your y values by 3, and look at that's like it's like you stretched it up. So you see how like they're all moved up. Vertical stretch. Next one, you're gonna see it's less than 1, so it's gonna be a shrink. I'm gonna do the same thing real quickly. I will use the same points: 0, 0, 1, 1. It's a little tricky, but 1, 1, 3, 3. Negative 1, 1, and negative 3, 3. So same idea, it's on the outside, so we're going to multiply our y values by 1 over 3. So by 1/3. So let's start here. 3 times 1/3 is 1, so it's going to move down here. 1 times 1/3 is 1/3, so it's going to be like right here. 0 times 1/3 is 0. 1 times 1/3 is 1/3. And then 3 times 1/3, the y value, 3 times 1/3 is 1. So it looks kind of like this. Right, and that's a vertical shrink. We've shrunk it, we made it smaller. We like crushed it down. So that's how those work. That's a non-rigid transformation because you're multiplying by a number. It's called a dilation otherwise, or stretch and shrink. Okay, one last one. So this is the same thing, but it's on the inside. So here's this gray graph. All right, I'm gonna point out a couple points here. So let's point out this point right here. That point is 1, 1. I'm gonna point out this point right there. That is 0, 2. And is there any other point that's good? Maybe this point right there. That is negative 1, 3. So same idea, but a little differently. So here's this graph, this function here, right? We're doing it. They give you the graph, but it doesn't matter. We're doing this to it. So we're gonna do the exact same concept. This is on the inside, so it affects the x values. And we're gonna do the opposite. Now, opposite's tricky. It's opposite operation. So we're going to do opposite operation. So in this case, notice how it says, it looks like you're saying multiply by 1/2. We're going to do opposite operation of that. We're not going to multiply by 1/2, we're going to multiply by 2. So in this case, so we're going to multiply by, so we're going to do the reciprocal, multiply by reciprocal, basically. So we're going to multiply by 2. If it was like 2x, you'd multiply by 1/2. If it was, yeah. So we're going to do opposite. So opposite operation. So instead of multiplying by 1/2, we're multiplying by 2. So we're going to get all my x values, negative 1, 3, 0, 2, 1, 1. And then all the x values here, we're going to multiply by 2. Because on the inside it's x, you do the opposite. So instead of multiplying by 1/2, you flip it, multiply by 2. So this becomes negative 2, 3. This becomes 0, 2. And this becomes 2, 1. And if I graph those, negative 2, 3. 0, 2 stays. And then 2, 1. So it looks a little like they got a little fatter on the outside. So it looks like this. So it's kind of like that. That's what happens. You made it wider. Because remember, 1/2 looks like you generally make it smaller, but this is the opposite. When it's on the inside, right, you do the opposite. So a b greater than 1 is actually a shrink. It doesn't make it stretch, it shrinks it. And a b greater than 1, less than 1, is a stretch. That's what happened here. Look, if we stretched it horizontally, right? We stretched it along the x value, so it's like wider now. So it's a stretch. So that's the idea. We'll do more of it in class.